evaluate the definite integral, the answer will be a number. And so when we use substitution, we will not need to rewrite the antiderivatives in terms of u, but we will change the upper and limit of integration in terms of u as well. In this case, the exponent is x cubed and the base is 2.1. So we let u be the exponent only, x cubed. Du is therefore 3x squared dx. And so dx is du over 3x squared, where we isolate dx. But also, if u is x cubed, when the lower limit of integration x equals 0, u is now 0 cubed equals 0. When the upper limit of integration is 1, u is now 1 cubed, which is 1. And so we will replace the lower limit of integration to u equals 0. Coincidentally, the lower limit of integration is still 0, and the new upper limit of integration is still 1. But these 0 and 1 are now u, not x. X squared, 2.1. We replace x cubed with u. And we substitute dx with du over 3x squared. And we see that x squared canceled out. This is the integral from 0 to 1, 2.1 to the exponent u du with 1/3 as a constant multiple. We cannot combine this 1/3 with the base 2.1 because this 1/3 is the constant multiple and 2.1 is the base. Don't forget that 3 in the denominator means the factor 1 over 3. 1/3 is the constant multiple, so we rewrite this. The antiderivative of 2.1 to the u, which is an exponential a to the u, is a to the u. A is 2.1, the base, divided by ln of a. Again, a, the base, is 2.1, plus c. We know that c will cancel out, so we will not need to rewrite c. We then evaluate this as 0 and 1. If we evaluate this antiderivative at u equals 1, we have 1 over 3 times ln of 2.1 times 2.1 raised to the 1 power. And if we plug in 0, we have 1 over 3 ln of 2.1 raised to the 0 power. And don't forget that we are subtracting the 2. And so the answer is 2.1 over 3 ln of 2.1 minus 2.1 to the 0 is 1. 1 over 3 ln of 2.1. 2.1 minus 1 is 1.1 over 3 times ln of 2.1 because 3 times ln of 2.1 is a common denominator. This is the exact answer. The numerical approximation up to 4 decimal places, 0.4942. Usually, we need to provide the exact answer, unless the question specifically asks for the decimal places. Next, the integral of e to the 1 over x squared dx from x equal 1 to x equal 2. We see that there is an exponential term e to the 1 over x, so we let u be 1 over x. Du is negative 1 over x squared. This is because 1 over x is x to the negative 1, using the power rule for the derivative, because du is the derivative of u. We bring negative 1 to the front, and then we lower the power by 1. Negative x to the negative 2 is negative 1 over x squared. Don't forget the differential dx. Dx by itself is negative x squared du, where we isolate dx. Since this is a definite integral, we will need to evaluate the new limits of integration. When x equals 1, u is 1 over x, but x is 1, which is 1. When x equals 2, u is 1 over x, but x is now 2. This definite integral is now rewritten as, in terms of u, the lower limit of integration is now 1, but the upper limit of integration is now 1/2. E, we replace 1 over x with u over x squared, and we also replace dx with negative x squared du. There's a factor of x squared on top and bottom, so they canceled out. We end up with a -1 as a constant multiple because of the negative sign. The integral from 1 to 1/2 of e to the u du. This is negative. The antiderivative of e to the u is e to the u. No need to write a plus c because this is the definite integral, but we evaluate it at u equals 1 and 1/2. Plugged in 1/2, we have negative e to the power 1/2. Plugged in 1, we have negative e to the 1. Don't forget that we are subtracting the 2. So the answer is minus e to the 1/2 power minus negative e, which is negative e to the 1/2 plus e. So the answer is e minus e to the 1/2 power. This is approximately 1.0696 rounded to 4 decimal places.